So hello everyone and welcome back to a brand new video, and in this video I will cover problem D, that is count GCD from CodeTon round 3. I already made a video on problem C, so do check it out if you guys haven't. Now let's move on to the solution. Before we move on to the solution, I want to take a small break and tell you guys about Newton School's Premier Coding Contest. So as all of you guys love CP and all of you guys love to code, this is a great opportunity to show off your coding skills and also win some cash prizes. There are prizes worth rupees 30,000, and along with this you can also win some free coding courses or also grab some internship opportunities, right? So for this reason only, Newton School organizes this contest every month on a global scale, so you can also benchmark yourself where you are lacking or where you are standing compared to other students. So this month it will be on 27th October. It will be around 2.5 hours starting from 9 p.m. and it is absolutely free to sign up for. So there will be a link down below, so do check out that link and sign up for the contest for absolutely free. Yeah, so let's move on to the solution now. So in the problem, we have been given an array A of size n, where n can be up to 10 to the power 5. So something like A1, A2, A3, so on up to an. But this 10 to the power 5 is not the actual bound, and we will see later why. So given this array A of size n, we have to construct a new array B of size n, B1, B2, B3, so on up to Bn, such that every element Bi must lie from 1 up to m. Here value of this m can go up to 10 to the power 9. And secondly, for every index I, GCD of B1, B2, B3, so on up to Bi should be equal to Ai. So these are the two conditions, and given these two conditions, we have to count the number of ways to construct array B. And as the number of ways can be large enough, we also have to keep a modulo and do all computations under a modulo. Also going forward, I will express all the numbers in terms of their prime factors because we are dealing with GCD here. So it will be easier to understand and like solve the problem if we express all the numbers in terms of their prime factors. So let's move on with the solution now and see the observations. First of all, let's try to see the second condition. So the second condition says that my every element GCD of B1, B2, B3, so on up to Bi should be equal to Ai. Or we can say that GCD of GCD B1, B2, B3, so on up to Bi minus 1, and my element of Bi should be equal to Ai. And this term is just equal to Ai minus 1, right? Because GCD of B1 so on up to Bi minus 1 is equal to Ai minus 1. So I can say that my GCD of Ai minus 1 comma Bi should be equal to Ai. And this gives us the first observation. The first observation is that my every element Ai should be a divisor of Ai minus 1, right? So the first observation is every element Ai minus 1 should be divisible by Ai, right? Because GCD of Ai minus 1 comma Bi is equal to Ai. So Ai is a divisor of Ai minus 1. So every element Ai should be divisible by Ai, right? That is the first observation. So let's move on to the second observation now. The second observation is that array A will only have 30 distinct elements, or not 30, around 30, right? So approximately 30 distinct elements. Now why is it so? Because if you think about that, your elements AI can only be up to 10 to the power 9, and all the elements up to 10 to the power 9 can be made with just 30 prime factors, because 2 to the power 30 is around 10 to the power 9 itself, right? So any number up to 10 to the power 9 can be made with just 30 prime factors. So even if your element A1 is 2 to the power 30, if you think about your element A2, either your element A2 will be equal to A1, or your element A2 will be a factor of A1, right? For example, let's say your element A2 is 2 to the power 29. So if you keep doing this in just 30 terms, we will reach 1, right? And you cannot decrease this any further. So your array A will only have 30 distinct elements. Elements can repeat, but in total it will have just 30 distinct elements. So you just need to do computation for 30 distinct elements. That's why I was saying here that n is up to 10 to the power 5 is not the actual bound, because there will only be 30 distinct elements. So let's move on to the third observation now. So for third observation, let's try to compute the possible values of BI, right? So we have our array A, we have AI minus 1, we have AI and some other elements, right? To compute the value of BI, we only need two elements, AI minus 1 and AI. Why so? Because we know the formula for this. Here is the formula, right? GCD of AI minus 1 comma BI is equal to AI. So we know GCD of AI minus 1 comma BI is equal to AI. So we just need two values, AI minus 1 and AI, to compute the value of BI. So there can be two cases. The first case is case 1. If your AI minus 1 is equal to AI, in that case, your formula becomes GCD of AI comma BI is equal to AI. Now, what are the possible values of BI here? It is easy to see that any multiple of AI will work, right? We can use AI here, we can use 2 times AI, 3 times AI, 4 times AI, anything will work until we are less than equal to m. So the number of possible values is how much? This is just equal to multiple of AI less than equal to m. And the number of these multiples are how much? This is just equal to m over AI, right? So that is case 1. When your AI minus 1 is equal to AI, then we don't need to do anything. The possible number of values of BI are just equal to m over AI. So now let's move on to the second case, which is the tougher case, I think. That is case 2, when your element AI is a factor of AI minus 1. For example, let's say your GCD of 2 into 3 into 5 into 7 into 11 comma BI is equal to 2 into 3, right? Here this is your value of AI minus 1, and here this is your value of AI, let's say, right? Here as you can see, AI is a factor of AI minus 1. Here also you can see that possible values of BI are how much? Possible values of BI are equal to multiple of AI less than equal to m, that is just equal to m over 2 into 3. But in this case, your AI is not equal to AI minus 1. So not all the multiples will work, right? Not all multiples will work. For example, let's say your BI is equal to 2 into 3 into 5. If we use that here, you will get GCD of 2 into 3 into 5 into 7 into 11 comma 2 into 3 into 5. This is equal to how much? 235, you will get 235, which is obviously not equal to AI, right? But 2 into 3 into 5 is a multiple of 2 into 3, or you can say multiple of AI. But still it is not working. So in this case, not all the multiples of 2 into 3 will work. So we have to filter out some multiples, and to do that, we will use a method called inclusion exclusion. So there is a method called inclusion exclusion, and we will use this to filter out the useless multiples. Now, how do we do this? So let's look at the example once again. So we have GCD of 2 into 3 into 5 into 7 into 7, 11, comma BI is equal to AI. We know my BI is of form K into AI, right? That is, BI is a multiple of AI. Now there are M over A possible values of K, right? Because there are M over AI possible multiples of AI. But not all of them work. So we have to filter out values of K that work. And to do this, we will define something called useless factors. These are just factors present in AI minus 1 over AI. So here it will be 2 into 3 into 5, 7, 7, 11 over 2 into 3. So we are left over with 5, 7, 7, 11. So the number of prime factors here are how much? We have 5, 7 and 11. So these three are the useless factors. So if any of these factors are present in K, right, it will disturb our AI, right? So my element BI is equal to K into AI, where K does not contain useless factors, right? I hope it makes sense now, because we have GCD of AI minus 1 comma KAI equal to AI, right? So if my K contains useless factors, my AI minus 1 already contains useless factors. This useless factor will also come into AI, right? And we obviously don't want that, right? So I want to count the multiples of AI such that my K does not contain the useless factors. Now, how do I do this? So to do this, I will use inclusion exclusion. So I have to filter out the multiples that contain useless factors, and here they are 5, 7, 11. So possible number of multiples are 1, 2, 3, so on up to M over AI. That is M by AI possible multiples. Now I have to remove multiples that contain useless factors. And in our example, the factors are 5, 7 and 11. And to do this, I will break down the problem into steps. So in step 1, I will remove all multiples, or I will remove all multiples from 1 up to M over AI that have factor of 5. How many such multiples will be there? It will obviously be from 1 up to M over AI. We just have to remove all the multiples of 5. That will just be M over AI divided by 5, number of multiples of 5. Same step we can do for 7. So step 2, do the same thing for 7. So it will be number of how much? It will be M over AI over 7, right? So we will do M over AI minus M over AI upon 5. Here we will do M over AI minus M over AI upon 7. We will do the same thing. We will do same thing for 11. So we will do M over AI minus M over AI upon 11. So I hope you are able to see the pattern now, right? But still we are not done. Why so? Because let's think about 35, right? 35 is 5 into 7. So in step 1, we removed all the multiples of 5. So 35 was removed in this. Also in step 2, we removed all the multiples of 7. So 35 was also removed in this. So 35 was removed 2 times and we only wanted to remove it 1 time. So we have to fix this, and to fix this we will add 35 back again. So what I will do is, in step 4, we will add back multiples of 5 into 7 because they were removed extra. They were removed twice. So we have to add them once back again. So my value will be now how much? It will be m over ai plus m over ai divided by 35. So we added back the number of multiples of 35. We can say the same thing for 77. 77 is 7 into 11. So it was removed in step 2, right? 77 was removed in step 2 and 77 was also removed in step 3. So we have to do all same thing for all the multiples of 7 into 11. So step 5, add back multiples of 7 into 11. It will be m over ai plus m over ai divided by 77, or you can say 7 into 11. And you do the same thing for 11 into 5, right? So m over ai plus m over ai divided by 55. But we are still not done. Why so? Because let's look at 5 into 7 into 11. If we look at this, if we start from step 1, 5 into 7 into 11 was removed in step 1. It was removed here. So I will say minus 1 here. It was again removed in step 2. So I can say minus 2 here. It was again removed in step 3. So I can say minus 3 here. It was added back in step 4, right? Because 5 into 7 into 11 is a multiple of 5 into 7. So we added back here. So counter here goes to minus 2. It is again added back in step 5. So it goes to minus 1. It is again added back in step 6. So we again have a counter of 0, right? So in step 6, now we have a counter of 0. So it was neither added and neither removed, right? But we want to remove this, right? Because 5 into 7 into 11 contains useless factors. So we want to remove this. So in step 7, we will remove all multiples of 5 into 7 into 11. This is just equal to m over ai minus m over ai over 5 into 7 into 11, right? And this is the entire process of inclusion exclusion. So if you try to see the pattern here, whenever our number has odd number of factors, right? Here we have a single factor 5. So we remove the factors. We have 5, 7, 11. These are odd number of factors. So we remove it. And when we have even number of factors, for example, 3 into 5, we have 7 into 11, right? 2 factors. We have 11 into 5. Then we add back the multiples. And in step 7 again, we have 5, 7, 11. These are odd number of factors. We again remove the factors, right? So that is the entire process of inclusion exclusion. So whenever we have odd number of factors, we will remove the multiples. Whenever we have even number of factors, we will add back the multiples. So that is the entire solution. So if I run a summary again, so I will summarize it once again. So initially my answer is equal to 1. So I will start for every index from 2 up to n, right? If my element ai is equal to ai minus 1, then I can just do answer is equal to answer into m over ai, right? Because in this case, there are no useless factors. So I don't have to filter anything. No useless factors. But otherwise else, I have to count the useless factors. So I will run inclusion exclusion. In this case, form all possible combinations of useless factors. Right? Form all possible combination of useless factors. Useless factors are found using ai minus 1 over ai. So form all possible combinations of useless factors, and if number of factors are even, add their multiples. Otherwise, if they are odd, remove their multiples. Right? That's why for 5, 7, 11 they were odd, so I removed their multiples. For 5, 7, 7, 11, 11, 5 I added, and 5, 7, 11 I again removed. Right? I just saw the parity, and these are the only possible combinations for 5, 7, 11. Right? There are no more possible combinations. If there were, you have to make them also. So make all the possible combinations, count the number of factors. If they are even, add their multiples. Otherwise, remove their multiples. And in the end, just do answer is equal to answer into filtered multiples, right? That you have just filtered out. That is the entire solution. So if you guys want to see the code for this, here is the code. So I have a solve function. I will take n and m. I will check if there is any index where v of I is not a factor of vi minus 1, then the answer is 0. So I will just do that. Otherwise, my answer is equal to 1. I will start from I equal to 1 up to n. And if my v of I is equal to v of I minus 1, my answer into m over vi. So in this case, there are no useless factors. So this is the first case. Otherwise, I have to find the filter of multiples. So I have wrote a function here which will give me the multiples. So get multiples. Here I find vector log of factors. This will give me useless factors. So these are the useless factors. This entire function is just inclusion exclusion, right? This is just inclusion exclusion, right? The total number of multiples are how much? These are just m over ai, right? So from 1, 2, 3, so on up to m over ai, right? So then I will run a function that will find all the combinations. So in this case, I am just iterating over all possible combinations of useless factors, right? Then this parity gives me the number of factors in the current combination, because I need to find this even or odd, right, to add or remove. So this parity will give me if the number of factors are odd or even. Then I will just like find the multiple of all factors, and in the end, if my parity is odd, I will do result minus total multiples over the term. Otherwise, I will add the number of multiples, right? So that is the entire solution, and I will just multiply them into my answer and then print out the answer. And that was the entire solution. So if you guys have some doubt, feel free to join my Discord server. I'll be more than happy to answer your doubts there, and I will see you guys in the next one. Bye bye.